and take it away.
All right, thanks. Sounds good. Okay, welcome everyone. So today we're going to move from using tools to characterize flexible metamaterials using floppy mode instead of self-stress towards design. And I'm gonna show two methods to design. One, inverse design, that you can use a optimization algorithm for, and the other, which I've worked on over the past few years using combinatorics. This is on the menu today, and tomorrow we're going to treat. Today we design metamaterials machines, and tomorrow we realize that we don't fully understand the machines we design, so we have to describe them. And often this happens in the nonlinear regime. So tomorrow we'll study the nonlinear regime, and we'll study also what happens in the interactions between many unit cells. And so that's basically what we'll cover on this. But before that, I'd like to come back to this and ask whether there is any question on this, or even on the lecture of yesterday, if there's remaining questions or things that were unclear. So as a reminder, we essentially introduced a tool to characterize in how many ways these objects, for instance, can deform without stretching any of the bonds. And I ask you to try to do that numerically through this compatibility matrix. And yeah, so if there's any question on what I discussed yesterday or on the exercise, we can address them now. Yeah.
I don't understand completely the meaning of the colors of the picture.
This is just aesthetics.
Okay.
Yes. Yeah. So basically, you have rigid triangles, and they can freely rotate around them, and then rigid bars that can also freely hinge. That's pretty much it. Okay. If not, I'll post the code to do that later today, so you still have time to try by yourself. And if you want to try, you can also just come to me or to actually Ryan, who also knows how to do that. Okay.
So I have a question. The compatibility matrix that you are calling there, is it related directly to the dynamic matrix? Because
say it again.
Is it related to the dynamic matrix? I think
yes.
you showed it.
Well, you can use the compatibility matrix to build the dynamical matrix.
Okay.
So the compatibility matrix is this one. So this is the displacements of the nodes. So U, I mean, you can write like this. So this is a matrix. So U is typically, displacement vector of all the nodes. So imagine you have n nodes, so you have like a horizontal component, vertical component of node 1, node 2. Right? So this is typically a vector like this. And this is the elongations of the bonds. So this typically would be the strain. So imagine you have m bonds and n nodes. Then you have this matrix that is a rectangular matrix of m by m that relates those two. Okay? And actually the dynamical matrix is, you can construct as follows, as the product of the compatibility matrix times the transpose of the compatibility matrix. Right, so typically when you have to write like Xiaoming did yesterday, she wrote it on the fly directly, but if you don't know how to do that, you first write this one, then you write the transpose, and then so you get your dynamical matrix. Okay. Yes, for instance, if we take the example of Xiaoming yesterday, just a 1D line of springs, right? So here you have a U1, U2, U3, U4, right? Then you would have elongation in the spring epsilon 1, epsilon 2, epsilon 3, right? So here what you would do is write epsilon 1, epsilon 2, epsilon 3 equals okay. And then you know that, for instance, the strain in the spring, strain epsilon 1 is due to a displacement to the node U0, right? So here you would have a 1. Positive displacement leads to of -1, right? Then you have 0, 0, 0. Then if you look at the strain in no, sorry. You also have a displacement of the node 2. So here you would have a 1, right? Here you have a, then epsilon 2 would be 0, -1, 1. And here 0, 0, -1, 1. So that's how you build your compatibility matrix, just by looking at which displacements will create a strain in the bond. And essentially, the exercise here was to ask the computer to do that for you. Once you, yeah. And so, if that's essentially it, right? Does it help? Yeah. Okay. And of course, I always do it in 1D because it's easy. That's why in 2D it's nicer to ask the computer. Yeah. More questions? Okay. So just so let me come back to the outline today. So design. So basically what I showed yesterday, we discussed a lot about this auxetic, so negative Poisson ratio. And what I told you is that, yeah, this is one of the most basic way to change shape. This is an example, for instance, in 3D, where you have this object, you compress, it shrinks on all sides. And this is due to some pattern of internal rotations, as we discussed yesterday, right? And actually, the basic mechanism here is actually quite similar to this one here. And the way you can think about this mechanism here is you shouldn't look at the holes, but you look at the material instead. And one way you can abstract this is by basically abstracting those as squares that are connected by their vertices, right? So pretty much something like this. Something like this, like a tiling of squares. And when you start to compress them, the square rotate. And this essentially will create this negative Poisson ratio effect that we have. Right? And so I told you yesterday that we don't really know how to design, so we always have to start somewhere. And I guess the examples I will discuss today all start from this. So what we'll do today is just make variations of this to enrich the library and have more interesting shape changes than just these purely auxetic shape changes. And so one thing, for instance, you can do is make it hierarchical. That's what we did here. So you have squares within the squares, and if you do that, you still get this kind of boring auxetic behavior, but you get it in 2 steps. So that's kind of cute, right? And so that's what we have here. Effectively, what you get a first step, it folds, and then you get somehow a new structure that can fold again, right? So that was the trick, but somehow it's still very limited in terms of shape change. You can also do it in 3D. So then you have to find a way to tile not squares, but rhombi. And then you can also get, for instance, 2 steps, right? That's it. Right? That's one way. if we don't do the rotating square, some people, this was actually the first metamaterial paper of Itai, I believe, on Miura-Ori. This is another mechanism that people also find very nice to start from. So this kind of the origami counterpart of rotating square, if you wish. And so this is, a kind of building block. So it's more, I don't, if you want to do that, you have to do a spherical trigonometry. So you have to be smarter than I am, but you can do it, and people did it, including Itai. And so here you get a similar effect, which is like auxetic, so this object can really deploy. And actually, this geometry was first proposed, I think, by this aerospace engineer, Miura. And then based on that, for instance, this is, I think, a paper by Guest, where you take this origami, you glue it, and then you have like 3D material that can have a big setting. So that's essentially one way in which you can do that. But again, it's still a kind of limited shape change, right? Because it's just auxetic period, right? What can you do if you want to do a bit more, right? Well, you can come back to this rotating square, and then here, what these people have proposed was to actually use this idea of hierarchy, but then, spatially tailor where you put the number of hierarchy that you put where, right? So if you put less hierarchies, if you do just homogeneous cuts, like the same number of cuts, the same number of hierarchies everywhere, and you get a homogeneous dilation. So again, this negative Poisson ratio effect. But again, here what they propose is that you need not do that. And so if you here do, less hierarchies, well, then you can get a gradient of shape change, and you can get a more interesting shape that's just not purely homogeneous dilation, but a gradient of dilation. Okay. And so maybe this starts to get us somewhere, right? Because that means that if we pattern, clearly if we pattern where we put the cuts, or how the cut look like, then we can actually control and get more interesting shape changes. Okay? And so the question really is now, how do we do this, right? So what approach, which tools can we use to actually control the type of shapes that we want, right? I'm going to discuss briefly this one first, optimization. So when you have an optimization problem, you have to define a target, like a cost function that you want to minimize. And then you refine your parameters to get it. And that's what these people, Gary Choi and Mahadevan did a couple of years ago. But again, you see that it all starts from a very basic, this kind of basic geometry. So they have this rotating square, which when it folds, gets into a small square, auxetic again. But here what they ask is, hey, what if I want to start from the square, but unfold to a circle? Okay. And to do that, they propose to distort the pattern. Distort the squares into parallelograms, essentially, so as to minimize the distance between the actual deployed red line and the red line that they want at the end. So they really have to do that. So then what they did, which was interesting, was to actually define this optimization problem. But there's a catch that you cannot change the length of these parallelograms as well, because as we discussed yesterday, if you don't do that, if you don't guarantee the foldability, you get a frustrated object that will not be able to unfold. Okay. Okay. And so to do that, they formulated a bunch of constraints. And I won't explain all the constraints here, but basically the constraints relates to be able to unfold and fold adjacent squares. And so then what they do is they minimize then the distance between the perimeter or the outside of the object and the object that they want. So that's really what they minimize, given all those constraints, with some extra smart trick to have a smooth gradient to optimize, not something that's very rugged. Okay, and so doing that, they actually did a very basic optimization, and they could show that you can get on-demand shapes. So to me, that was one of the first examples where you can really get, you program the shape that you want, and then somehow you have a MATLAB code that does it for you, right? But again, I think the types of shape they can get is also fairly limited. And
So sorry, the
yeah.
minimization was on the angles between the squares and on the distance?
Yes. So I think here the variables were the angles of the squares, the edges, so all the parameters that define your quads. But for instance, here you have to keep A equals to B if you want them to fully fold. If A is not equal to B, you're not going to be able to fully deploy or fully fold. So that's why, for instance, you need this constraint. Same here for the sum of the angles. So at each vertex, the sum of the angles should add up to 2 pi. So that's kind of the constraints they maintain. Yes?
What is C?
C? I'm not sure. I'm not sure what C is. Some parameter of the tiling, but I'm not sure what C is. Yeah. I think it's maybe the last constraint is to make sure the quads don't overlap. So maybe it's something that keeps track of the folding angle, the maximum folding angle that you want to allow. But I'm not sure exactly how. Yeah. So they actually showed you can also extend that to 3D shapes. But again, so here it's I think quite interesting because you have an example of tool you can use to design shape-changing objects. Okay. And well, it's limited, for instance, to smooth curves. It's limited to a single shape change. It's the stroke with which you deploy is also limited by the mechanism you use. So there's a lot of limitation. And of course, they started from this rotating square, Kirigami pattern. But it's so. Well, I think they in their paper they of course showcase as many shapes as they want, but I'm sure they couldn't do anything they wanted, right? So I'm sure that you have some limits. For instance, it could be hard to have more wiggly, it would be hard perhaps with this approach to have more wiggly or textures, for instance, right? Like I will discuss later. Yeah. But again, I like this paper very much. I haven't done the work myself, so I don't know. I don't know at which point you run into a wall with this approach, but I'm sure there is a wall at some point. Yeah.
So I think as long as you allow the strips to be as thin as you'd like, so that you can get a ratio of opening as large as you'd like, so a factor of increasement of size.
Yeah.
They should be able to realize any shape. It's going to stop at the point where the paper doesn't allow you to do the cuts. Create such a thin strip.
Yeah, I think the more unit cells you allow, the more shapes, gradients in the shape that you can get, probably. So there's I think, and actually discussed that the less number of squares you use, the farther away the less you kind of satisfy your cost function, right? But yeah. Anyways. Yeah. All right. And so, I just wanted to cover that example because I think it's quite interesting, and I think in general, it's not so often that you have like such a toolbox to design nonlinear shape changes. So I think it's nice. But for the rest of the lecture today, I'm going to talk about combinatorial design, where we will design for materials, complex materials with on-demand shape change. Okay. And so to do that, we'll start from this building block, which is the unit cell of the rotating square that we discussed, and that's what we used later. And I'm going to discuss a few examples where you can actually expand on that. And so the first one is actually done by Anne Meutzer, who was a PhD student in the group of Martin van Hecke. So I was not involved in this work, but I still think it's interesting to cover. And so the idea is to, replace those squares building blocks by triangular building blocks. And then you have a very similar folding mechanism, but instead of now having a square tiling, you have a triangular tiling. Okay. Then I will discuss how you go to 3D. So basically, you take this unit cell, but you duplicate it and put it out of the plane, and then you get a cubic isotropic building blocks. And then lastly, I will discuss something we recently introduced, which is if you want to get more than one shape change, you remove one constraint, and then you see that in all these examples, you only have one mode of deformation. But here, you actually have one, which is similar to the one before, but also another one, so you have two, okay? And so I'll cover, I think, those three examples and show you that they are of increasing complexity and also offer interesting possibilities for shape changes, okay? So let's first start with the example of Anne. So the idea is to use that building block. And I think what's interesting about this building block is that, well, it folds like this or like that. It's the same folding motion, right? But then, so this you can tile in a triangular lattice as you want. But of course, if you want this tiling to deform, to have a floppy mode, you need to make sure that the deformed building blocks actually fit together. So what you do to do this is you actually take the tilings that are deformed and then, you play a puzzle essentially, right? And that's what you get. If you want to help you solve the puzzle, what you can do is actually map this onto a spin problem with arrows. And then this question of compatibility, kinematic compatibility, just comes back to looking at identifying the ground states of a spin problem, okay? And so that's what you can do here. At every point, you can look at the arrows and you can see whether the arrows fit. And if they fit, you're happy. That means you found.
There's a question there.
Yeah.
Sorry,
Yeah.
I didn't attend the previous lectures. Maybe it's obvious thing, but do you know ahead when you release a constraint how many, how they generate, how many possibilities of configurations, basic configurations you have? I mean, how many ground states, simple configuration you are going to have, or is like you release the constraint, you kind of try and see.
Yeah, no, that list, finding the number of ground states is part of the question at the end, right? Oh. Yeah, so that's really part of the puzzle. And actually, I'll show you in the cube example that can be a tough nut to crack, right? To find a ground state of a spin
so
problem.
There's no mathematical calculation that 4, 5, 6, 7, 10 how? There's no fixed number.
You can mathematically formulate lower bounds, upper bounds, and exact formulation based on combinatorics, essentially. Like you do it, I think, for any Ising problem, right? So you can do it. And here we can do it because there's some, in those cases, in the two first examples I'll show there, you can do it because there's this parity symmetry that I will discuss because you see that, actually there is order in the arrows. There's always this order, this is either ferromagnetic or anti-ferromagnetic, that allows you to somehow, that saves you at the end to solve the states there. Yeah. So if you find it, then, if you find the lattice that you could tile, you can count all the possible options by doing some counting combinatorics. And if you like, you can print one sample and see that it works. And that's what they did here. And what's interesting, perhaps, is that, okay, it's still something that is auxetic, but somehow the pattern is highly complex because you have many possibilities, right? One thing I want to quickly mention is that what's interesting about that example is that you have different types of building blocks. So here, if I put a triangle that is oriented up and then next a triangle that is oriented down, what you have, you can do that, but you can also put a triangle that is oriented at 60 degrees, and you see that you can make, for instance, a chain about this. What's interesting is that on top, when you put those two guys, you see you have some kind of anti-ferromagnetic order where the arrows are staggered. But if you do this in the bottom, you see that you can have ferromagnetic order. So what's interesting about this example is that depending how you put, how you tie, for instance, the strip, you can have a chain that has, alternating or on-demand ferromagnetic or anti-ferromagnetic order, right?
Can I ask,
yeah.
how do you define the direction of the spins based on the topology of the?
This is based on kinematics. So you know, for instance, that this guy, the linkage inside here is a rhombus that will open. So typically, this will tend to, you know, the angle will tend to open here and open here. So this will, you can depict this on map 2 onto a spin that is here antiferromagnetic, right? And so that's what happens here. You see that here, if this guy starts to close, well, the next one will start to close because of the, you know, how the 4-bar linkage is. But now you see that if I have rotated my block, here, if I move, I have this bar. You see that this bar will constrain me to, will constrain this guy to move the same direction as this one. So you see that here, this building block is actually ferro. So here you see that they could make strips that have, you know, on-demand ferro and antiferro magnetic links. Yeah?
It feels like the order should be nematic and not vector, because you have a direction which elongates and a direction which becomes shorter.
No.
A rhombus has a
yeah,
deformation
but
which is
here
nematic.
in the way I map, you know, if I'm nematic, you know, this means like, you know, going right is the same as going left. So I have, you know, you come back on yourself when you rotate by pi. This is not the case, right? If I start to close this guy, you know, if I start to, or if I start to open this guy here, you know, this is different than if I open. So if I flip the arrow, I'm going to flip all the arrows, right? So you don't have nematic order here. I don't know if, I think my answer is not very clear, but
we can talk about it.
yeah. But anyhow, so here what you can do, for instance, that's what they did. They change, you know, the sum. You know, they make a strip where the sum of the ferro antiferro is different, and so that means that on the top you open this bond, and on the right you also open it. But if you now flip one of the unit cells, you can actually do the opposite, right? One way you can actually so I guess the point is in these systems where you have this 1 degree of freedom object, parity matters. So you have this really order antiferro or ferro that you can really play with to design objects. What's interesting perhaps to mention in passing is that you can actually know, one way to know that is to just measure the size of this strip here, black strip, and you know that the direction is going to be given by the number of segments you have here, whether the number of segments is odd or even. So just by looking at these objects, these strips or these loops, by looking at the parity of these loops, you can determine whether you're going to have the same deformation here and there or opposite deformation here and there, right? So, and I think, so that's what they, for instance, used to actually abstract it and think about the system. You just look at the loops of these additional bars that are inside, and you know that so long as you have even loops, you're going to be able to fold. But if you introduce an odd loop by, for instance, rotating a block, then you know that you have a loop, so you should come back on yourself. But if you come back on yourself with the opposite deformation, then you'll have some geometric frustration, and that's what they use to design here topological defects in this object. Okay. And that's it. So that's one way you can think of how, I guess, antiferromagnetic and ferromagnetic order kind of encode whether an object is foldable or not.
Sorry. So then you say frustration would cause topological defects. Is that what you mean?
Well, because here so if you have a odd if you look at this and you have an odd number of ligaments, you know that the deformation is going to be opposite on either side of the strip. So now if you close the strip and make a loop, if you have the left start of the loop wants to close and the right side wants to open, then the loop is not going to want to fold and it's going to be geometrically frustrated. Okay, and the reason why they did it, the reason why in that case they were interested in defects was to actually be able to the reason why it's topological is because you can just look at the loop, and you know that because the loop is odd, you will not be foldable and frustrated. Yes.
How many loops do you need to check to see if there is any topological defect?
One is enough. Yeah, that's you know, that any time you do a topological defect,
Yeah,
you
but
do one loop.
if I have a random network,
Yeah.
how many loops do I need to check to see if there's any topological defect?
If there's any topological defect, well, you know, if you want to know, that depends. Let's say you have your material here, right? And I don't know, your defect is there, right? You need to make a loop. You need any loop around that defect would do, right? So if you make a loop like that, you will find a defect. A loop like that, you will find a defect. But if you do this, you'll miss it, right? Yeah.
But there are also a certain number of loops you can make there.
Well, you can by eye, but you know, you can loop over all the loops, right? And check by eye or by a computer, right? So that's.
But there's no smart. So there's no smart way in checking all the loops, or
Yeah, no,
less than all the loops.
No, but that's typically, I think, a quite computationally cheap operation to check for loops, right? The parity of loops, right? So, yeah. No, I don't think you have a better way. No. And that's typically how you check for topological defect in general, right? You make loops, and you see whether your order parameter, you know, here in that case would be the parity of this order parameter. Okay. So that's a very basic example where, again, arguably this kind of shape change is a bit boring, but it's mostly auxetic. But what you get is somehow inside you can get more interesting texture because you can pattern locally whether you have ferro or antiferromagnetic order. So that means you have a bit more freedom still, right? And in the second part, what I will do is exploit a bit more that freedom. By using this in 3D, okay? And so to do that, I'm not going to make triangles, but I'm going to make cubes, but still cubes that have one way of folding. So this is, you know, the cube. It's anisotropic. I'm going to slide it over here. And one way you can realize it out of a material is, for instance, making this. And you see that here, if you have two building blocks. Let me see if the video. Ah, yes. So when you have two of these guys, they can fold together. And so that's nice. That makes up the first green cube I showed you. But there's an interesting, just as in the case of the triangles, we could actually rotate them to get more interesting features. It's the same here. If you put a building block, if you rotate it, I lost my mouse. Hopla. Ah. Okay. If you rotate it, you see that two of those guys can actually also fold in unison, right? So that's nice. And now again, you can start to play your puzzle, right? So now you have this. We have designed one building block, but we get 3 for the price of 1. Actually 6, because you see that now I had this one that can fold, you know, it can become thinner or fatter, and I can also rotate it in the X direction or in the Z direction here. And then you can ask the same. You can also ask yourself whether there is kinematic compatibility, right? So you take one cube, and then you want to tile another one. You have to make sure that they can fold. So you can depict whether they fold with this arrow here, and again and again. And here you see that now you have a puzzle to solve because there's only one option here. Right, so can you tell me which one is the good option here? Second green, yes, indeed. So that's how you make a tiling and so on and so forth. Right? So that's how you can do it. I will show you that here there's also this same parity antiferromagnetic order that's really useful, and actually that's what we use for design. So one way you can actually abstract this is by drawing cubes, you know, abstracting your cube, your real building block by cubes, where you have a little you know, white pad if it bulges out, and green and black pad if it bulges in. And again, here you can see that you have ferromagnetic order. So you see, if you have a slice, you see that here you can also design the next slice by making sure the arrows fit, and you can do it. You can do it here. So this is what happens if you tile a periodic one. So you see here, I have a black cube but reversed, a black cube reversed, reverse, reverse, reverse. So you see already that it's kind of this anti-ferromagnetic order that occurs. But here I can also, I don't need to use a red one, right? I can use a green, provided I choose it carefully that the deformations fit. Right? And so you can do it again, you can draw by hand and so on, and so on and so forth. And so you can do that, you can continue, and so on. But so here, so the question here is really, it's a bit annoying to have to every time to solve a puzzle, right? If you ask the computer, it actually explodes also with system size. So actually, you would want to have some way of counting and some way of determining what's you know, how many states you have. And really, to do that, we solve the combinatorial problem. We actually estimate lower bounds, upper bound, and so on. But the crucial, I think, ingredient that is really here responsible for the fact that we can solve it. Otherwise, it would have meant that we have solved the 3D Ising model, and people would have known it if we would have solved that, right? But here, there's an essential symmetry. There's this anti-ferromagnetic order that really makes your life much easier. You see that here, this fat gray arrow here is always having alternating arrows, which means that there is some form of holography, which means that if you know what happens at the side, at the you know, at the edge. Okay, is the sound still okay?
Yes. I have a quick question.
Yeah.
This reminds me very much of vertex models for Ising.
These are vertex models.
Okay, okay.
Yeah, yeah. In fact, for statistical mechanics in like 50s and 60s, people introduced very similar models, called vertex models, which were really, you know, kind of you know, objects like this, where you could also do some interesting statistical mechanics there. Yes, yes. And in fact, what we have is just a 3D version of it, in a way. We have in vertex models what's I think you can have, I think, different types, right? So for instance, you could have this, but you see that in this case, the sum of the arrows is not necessarily 0, but in our case it is. So that's also connected to these ice rules in spin ice, which because of our objects, because of the way our objects are designed, need to satisfy the ice rule. And I guess I've slid it into the carpet here, but the fact that you have the ice rule also constrains or limits the number of possible patterns of arrows that you can have. And somehow is also indirectly responsible for having this anti-ferromagnetic order.
Corentin,
Yep.
I have a question.
Yeah.
Since you can do this type of mapping between your pieces and spin,
Yeah.
could you be inspired in the knowledge that you have about the spin models, in the sense that you know about a lot about what happens if you put in different types of networks? You are always using this first neighbor network.
Mm-hmm.
Could you be inspired in the solutions that you know from statistical mechanics to change the way that they interact? Let's say put them in a different lattice, or I don't know,
Yeah.
creating long range. I don't know. I mean, I don't know if it's easy to do in a practical sense because they are kind of touching.
Yeah. I think, for instance, the first case I showed, what they run into is a problem that was already existing in StatsMech, so they didn't have to do it again, right? So I think what you said is, for instance, correct in that case. Here, I'm not sure it was actually existing. Like, why would you have this isotropic building block in the? So it was not, I think, in the literature, right? But I think if indeed it was, I think it could have been useful. I think in general, and what I don't know is that what I discussed later, when you have more interesting patterns, what I would like is some classification that tells me, whether a problem can be solved or not, right? And I haven't found that in the vertex model literature, but I think there might be. But I think it's a bit maybe beyond me. Or I'll discuss maybe the last example I show really is something that is a bit wild in terms of vertex models, because it doesn't have unitary deformations. You can have as many arrows as you want, for instance, and there it's a bit hopeless, I think. Maybe this case is sufficiently simple that we didn't have to dig into the literature. But I'm sure that if you come up with a new building block, you can find something that maybe has closer connection or relates more closely to models that are of current interest also in StatMech. Yeah.
Related to that, usually when you have an universality class, when you
Yeah.
think about this type of models,
Yeah.
can you map this, thinking about also in your case, having a universality class, even though you don't solve it exactly with the models, you know that there are phenomena that are linked between them?
Yep. I think here my basic answer is that yes, and I think here the universality class here has Z2 order, right? So Ising order, and so these things that have really falls into that class. So if you want to, if you would do the Linsberg-Landau theory of this system, you will, for sure here, you would describe it by some form of Z2 or Ising spin, right? So, and I think this kind of materials really falls into that class. Yeah. But I think, imagine you had, I don't know, Z3. You could imagine something that has some spins that can have actually 3 different values, not 2, yeah. So you could imagine that. So Z2 here is because the arrow can be left or right? But you could imagine some arrows that is this, and this. So Z3. Actually, we're
And
yeah.
also you can have something that's not square.
That's
the
a-
models
yeah.
in which they have in a different type of symmetry. There are systems in which, not thinking about spins, but thinking about structure, like strong titranate have many different configurations that are not Ising, but they could be mapping in things that will not be square like that, and with different type of errors. So
Yeah, actually, I have a colleague who does integrable system, a theorist, and he told me, I would love to have a chain of spin on U2, on the spheres. I don't know how to do that yet. Also, we have cold atom colleagues who could actually, with their tweezers, they could do Z3.
Yeah.
And so I think there's interesting connections there. Yes. But so far, all I'm discussing, at least this first triangle one, is I think Z2 Ising. But it's so easy to. Oh, it's so easy. If you're lucky, or if you search hard enough, probably you can find more that are also worthwhile exploring and interesting. Yeah.
Thank you.
Yeah. And so since we have this antiferromagnetic order here, we have this holography. We just need to worry about the edge, right? So that means that the faces of the cube determines the inside. So that means that if you want to upper bound, you don't have to think about the orientation of every single cube. So you don't have 3 to the L to the 3 possibilities, but you have less. You only have 2 to 3L cube, 3L square, right? But of course, this is if you decide to specify the faces independently. But there's only, these building blocks have some constraints, so you cannot choose anything, right? So actually, this is why this is still an upper bound, okay? And the lower bound that you can derive is just assume that one face can be arbitrarily free, and then you have no choice inside. So this is the lower bound is that you can determine one face only. and so that's why you here you have one possible lower bound. And what our colleague Yair Shokev and his student Eyal Tayomi did was actually to do the exact counting, and so they went nuts a bit and counting the whole number of possible options as a function of the system size for a cube, for instance, of 14 by 14 by 14, and it actually approximates the lower bound quite nicely. So that's it. So here I show you that with a bit more freedom with these anisotropic building blocks, you can do a bit of combinatorics and find interesting textures, both for the cube but also for the triangle. But where I promise you some design, and we haven't designed anything yet. Yes. Yeah.
Question.
Yeah.
So here you have one building block which you can rotate.
Yeah.
And then you ask the question of how many designs you can have which are floppy.
Yeah.
But in principle, if you had a few different building blocks, you could span all possible arrow configuration for this six faceted cube, and then you could construct any bulk.
But then you have less constraints, less symmetries, so you're a bit more hopeless to explore it, I guess, right?
No, but I think then you would have only one configuration for a random assignment of arrows everywhere in the bulk. You just say, okay, this is the building block for this assignment of arrows. This is the building block for this assignment of arrows.
Yeah. In fact, we started to do this, but it's not very efficient design. So you could say you start from a pattern of arrow, you choose your building block as you want. I think it's possible, but it's also it's a bit cumbersome for designing. I think I can give you more detail maybe offline, but yeah. But I think that's an interesting approach. That's kind of the counterpart of the optimization approach from Choi and Maha I discussed. Yes, but somehow it's still, since the system is highly discrete, there's no smooth gradient, so it's not very efficient to explore. Yeah. So let's see. We have a pattern of arrows that we can design. So I told you the lower bound is actually designing one face. So in principle, that means we can design that face arbitrarily free. That's what we did here with this smiley face. And I'm just going to show you quickly how we did that. So here we don't need the blue ones. We can just do everything we want with the green and the red. I told you that we have some, antiferromagnetic grid. So that's my antiferromagnetic grid. And you see that, so my grid is only having, if I only take these two blocks, I only have this pattern of arrows here. So it's really a staggered antiferromagnetic grid. And what you can see here is that whether I choose, if I choose a green or a red, I can actually decide freely what's going to come out, whether it's going to have black or white. And so, for instance, here, if I have if I have arrows coming in on the horizontal axis and coming out on the vertical axis, if I want something sticking out, I need to use this one. Right? For the same pattern of arrows, you see that if I would use a green, it would go in. Right? So now that's how I can. So that's what happens here. Right? If I do it. Same here. Now, if I use a green, if I just use a green as a neighbor, if I don't do anything, since we have this antiferromagnetic order, next to a black, I'm going to have a white. But by changing the color, making it red, I can have two subsequent black dots, right? And that you see, that's kind of how you can actually design. That's how you can design a smiley face, by carefully patterning your, you can basically escape the antiferromagnetic order by, combining green and red at will, and that's what we use here to design this smiley face. Okay, and so that's what you can do. And that's really, I think, underlying reason is that the lower bound for the number of states is really given by freely designing one face. And it's really connected to this antiferromagnetic order. So you can do this, you can print it. It's nice. since you have, and so here what we did, we use a slab that we repeat across. So that means that it's kind of this pattern is alternating. In the second slab, you have the opposite deformation and so on and so forth. So here, since we had 10 layers on the other side of the cube, it's like the anti-smiley. And since we stacked periodic layers on the sides of the cubes, it's like a checkerboard. Okay. Actually, we reprinted some recently because the paper of Ryan on machine learning, where we machine learned some of those, was accepted. So when you want to try to have a cover, you make a nice picture. So we actually printed the ML because it's been machine learned, and you see that we are still able to design letters. And that brings me to maybe a first exercise of today is design your own letter. So we're going to stop for 15 minutes, and I'm going to take your initial or favorite letter or favorite drawing and try to draw by hand the pattern of green and red that would make up your pattern. I don't promise we'll print it for you because it's a pain in the neck to print, but at least you know that. Yeah. So I suggest we just take 15 minutes for that. It's nice if I think just drawing on paper is useful, and then we can take a break after that. Yeah. Yeah.
And your local assignment of hours, you need to pick the corresponding block from this one.
Yeah, but these four are different.
Yeah, there's two options for each arrow combination. So the red or the green. And depending on whether you want the block coming out or in, choose one of the other.
Yeah.
So take the top right block. Okay? So that matches the arrow combination. Far right, green, and so it's more, but the far right green does not give you a block.
Actually, if you want, you can, during the break, let's take a 15-20 minutes break, but if you want, you can actually come and draw your letter, the cube on the board. And then we can play, after the break, we can just see whether we see any mistake, or we can see all the alphabet, whether alphabet is complete. Mm-hmm. Which one? The smile. This one. There's the smiley. This one. Yeah, but yes. This one. Yes? Before? No, the next. This one. Ah. All right. It's okay. Maybe 15, yeah.
I didn't understand why you said that with multiple building blocks it becomes very cumbersome, because I could imagine that there would be actually very few building blocks for such a cube, for example. Like the upper bound is 32, right? But then by rotation you can probably reduce it dramatically. So let's say more than 10 building blocks. I don't know if it's
Yeah.
easy to fabricate 10, like if I give you a random assignment of, oh, I want this facet to deform out and this one in, this one in. If necessarily you can come up with a solution, but at least if you do it with trusts,
Yeah.
like with, I think it should be.
We've done it in. We've done it in. We are doing it in 2D, in fact. And there, yeah. So what we do is, in 2D, we take for something that has no bars, really unconstrained many modes, and we add bars. Because in something that has no constraints, you can do anything, right? And then you add bars to just get the modes that you need, right? And yeah, somehow, for example, if you only keep on the pattern of in +1, -1, then we already have a solution here. That's this one, right? So I guess what we're trying to do is to have any pattern of arrows, like displacement, any magnitude, and then it becomes more tricky. But if you do only +1 and -1, then the solution is there. So I don't think you necessarily, So if you do your approach, probably you would
I
find.
would like a +1 and -1, but I also want to have a building block in which only one facet bulges out and all the rest bulges in. So I'm saying that if you had a building block that does that, and here you have building block of 2 in, 4 out holographic, but you could have 2 in, 4 out non-holographic, and you can have 3 in, 3 out in a few configurations. So if you had all of these individual building blocks, then you could also span for every random assignment of arrows in the bulk. You could there would be one solution of the building blocks inside, which would give you that, right? I mean, it becomes.
Say it again. Yeah.
So here, because the building blocks are holographic,
Yeah.
then you can also you can only get solutions for arrow assignment, including bulk, which are holographic.
Yeah.
And maybe also not any, I don't know, not any holographic solution. Right? This is like the lower bound, upper bound, and
But what you suggest is go beyond holographic then.
what I'm suggesting would be not necessarily.
Yeah.
Because if you could have a non-holographic building block, then you can also do stuff that are non-holographic.
Yeah.
I don't know if it's.
Yeah. No. We're doing that, but then maybe we're doing the step too hard, where we actually.
When you want to have also different amplitudes.
Yeah. And then that's the second example. Then it gets super messy.
And then with the different amplitudes, I guess that the defects can have charge, right? You could have defects that get up. Because in the +1, -1 example, with the amplitudes, 2 defects would cancel.
Yeah.
So it's like a Z2 class.
Yeah.
But if you have different amplitudes, that they would not cancel necessarily, right?
Yeah.
You could add, I don't know, 2 failed defects and then get a 2 failed.
Yeah, maybe.
Just the mismatch
Interesting,
would
yeah.
increase, right?
Yeah. No, interesting. Yeah, I don't know. Yeah, I think it's potentially interesting. Yeah.
I think, I guess my question is there anything particularly interest that we can do with the defects? Because we can find the defects and draw the line of the topological defect, or you could maybe say, okay, if I have different amplitudes, I can give you a defect of a particular charge. But then what? What do you do with it?
Yeah, that's always the question. That's always the.
You focused again on something that doesn't have defects, right?
Yeah, but I mean, it's not like the world is waiting for smiley cubes either, right? So I guess that's. But it's the. I think, yeah.
Could you change the slide to
Yeah, sure.
to show the different? The next one.
This one?
Yeah.
Yeah. All right. The slide with the C, okay. I've been asked with the slide with the C, but yeah, that's I think the same. Yeah.
So Itai actually had a nice paper in PRL on university.
Well, I guess people are still figuring. Right. So I guess we just resume. If you didn't get your letter and want to run it by us, feel free to ask me or Ryan, and we'll be happy to check. Anyways, so let's move on. I'm going to just briefly discuss in the time I have left the last part. So in the two examples I discussed, we really exploited ferromagnetic and antiferromagnetic order. So there was really order, right? And that's because we use this 4-bar linkage. So these building blocks really have only one folding mechanism. So N naught of yesterday is only 1. But as a result, it's a bit boring because you only have one shape. So you have an object that has only a single shape change, right? So the questions I want to ask is, yeah, can we go beyond this antiferromagnetic order? Can we go to like a slightly different, beyond the Ising universality class? And conversely, on the design side, can we get more than one shape change? Okay. And so to do this, the idea is to just use, our understanding of the Maxwell-Caledine counting. You count degrees of freedom and constraints. You find, N0 is 1. But if you remove one bar, what you get N0 is 2. So you have 2 floppy modes. And, one way there's many ways you could do it, but one way we did was to actually remove one bar here, and you see that this object can deform in 2 ways. Okay, and that actually was in this paper last year, and now Ryan just machine learned some of those, and the paper is going to appear in PRL in a couple of weeks. Because we don't have antiferromagnetic order, so we're a bit clueless in terms of. We cannot use parity, so we're a bit clueless in terms of quantifying all possible options. So we're just, back to just exploring, essentially, right? And so this is the idea. You have the building block. This is what the folding motion. You remove one bar, you get a new folding motion. And so what Alexi and David did here was to construct metamaterials out of those. And you can construct, you can arrange those. You can make, you can make cells that you tile later on. And the first question you can ask is, okay, how does the number of floppy mode grows with the system size, okay? And so that's what they did. And what you find is, interestingly, the Maxwell-Caledine counting tells you that you have many more states of self-stress than you have floppy modes. But somehow, depending on the tiling that you find, you have sometimes the states of self-stress grow a lot. So actually, your number of floppy modes grows. So here, the number of floppy modes grows with the system size. But in some examples, actually, the number of floppy modes is always 1. So it's always this mechanism. Sometimes, the number of floppy modes grow logarithmically if you make a quasi-crystal with this. And interestingly, you have an example where the number of floppy modes is actually constant, but more than 1. And so that is kind of, we call that Oligo-mode because it's a few, but more than 1. And that's interesting because that means that you have a material that has potentially more than 1 floppy mode, so more than 1 response, so more than 1 shape change, so more than 1 smiley face, essentially, ultimately, right? How do we think about this? Well, I told you that before we could map the deformation here on the vertex model, so we could put arrows, but now we have an extra folding motion, so we have an extra branch, right, in this diagram. And you see that now, before only had arrows 1 and -1, but now, since the arrows encode the deformation of the angles, you see that in fact you can have arrows that are beyond 1. In fact, they can go anywhere between, in Z, right? Yeah.
What is the meaning of the number of the triangle?
Yeah, so the arrows depict the angle change of each hinge, right? And you see here the hinge closes a bit, so the angle becomes a bit smaller. So that's why the arrows goes in. Same here, but here it goes a bit, the angle opens, so the arrows goes out, right? But here, when you see that this angle closes much more than this one, for instance. Which means that if you want to ensure kinematic compatibility, so if you want to ensure that neighboring building blocks fit, you still need to make sure that actually the arrows fit, right? So that's kind of a spin problem, except that we're beyond the Ising because we have, we have any level of arrows. It's also a weird lattice because there's a lattice that has a fifth branch, so this is a bit messy, right? We don't have time, but I had planned a kind of an exercise, which kind of a Metamaterials version of a Sudoku, where you would have to, for the lattice exercise we had yesterday, you can analyze the floppy modes by looking at the nonce space of your compatibility matrix, but it doesn't really give you a nice mode decomposition. If you do here the metadoku or the Sudoku metamaterial, you actually can get, you add your directed graph on top, and the arrows give you a nice decomposition of the modes in principle. And so that's kind of we don't have time to do it, but that's something I propose if you want, if you're interested to try to identify possible patterns of arrows. Here the solution yesterday was 4 modes and 3 modes here, or no, 3 and 4. And so you should be able to find at least 4 and 3 independent superposition, linear superposition of arrows, of patterns of arrows in here. Yeah?
The arrows, the fact that it was 1, 2, 3, 4, these are actually like integer relationships?
Yeah. And that's really because of the specific dimensions of your unit cell. If you distort unit cells, the angle change are related differently, and so then you're different. Then it changes the relations between your arrows. Yeah.
But go back one.
Yeah.
You had ones with 2 on the orange, and the angle on the right is the same as the bottom left, even though.
This is a different. What's your question?
I guess, from looking at the top left,
Yeah.
you say that the
this one?
deformation is high in the
corner.
diagonal.
Yeah.
But now, and it's a bigger angle in the diagonal than in the side.
Yeah.
But on the orange top, they look the same. It's 2, and the number of arrows is 2.
Well, I can also sum. I can also do a superposition of these two, right?
Right.
Yeah. So here I think I did a superposition, and I can divide this one by 2. So I mean, any linear superposition of these can work. In fact, that's also what makes it messy. In fact, yeah.
But for having any prospect of having a compatible global copy mode, does it need to be integer relations?
No, it need not be integer. It can be anything, but somehow that makes your life easier. I mean, at the end, this directed graph and these arrows, because we don't have this, parity and T-formality order, is a bit useless. The only thing it's useful for is that, it's a fun puzzle if you like Sudokus, and also it can give you a nice visualization of the modes, right? But it doesn't really help you more, in fact. So if you like puzzles, feel free to do that. What we did is we actually looked at the mode scaling, and we saw how there's one lattice that has 2 modes, and this was interesting because somehow we hadn't really seen that in the literature before. And so this is the lattice that had 2 modes, and this one, so this one is the rotating square mode, and this one is this weird mode that has a lot of deformation in the corner and a lot of deformation in the bottom up corner, and like virtually very small deformation in this diagonal here. And so that was interesting because that means that with one lattice you can have 2 responses. You can print it, and you can decide to actuate one mode by pushing with fingers on the side. So here I color the ellipticity of the pores to make the deformations a bit more apparent. And you see that here for instance, this is the first rotating square mode, and this is the other one that has this change of ellipticity across the diagonal. Okay. You can do more if you like this quasi-crystal. If you like quasi-crystals, you also can construct your quasi-crystal by a substitution rule, and you have these weird mode shapes that look like crosses. And this is interesting because the number of modes grows logarithmically, and so that's still something that is not incontrollable. It still has a few modes that you can still control. And so that's basically the one possible paradigm that you can use for having textures that are interesting in modes. And
color here means
color means
ellipticity?
Ellipticity, yes, of the holes, yeah. Or direction of ellipticity, staggered ellipticity, if you wish. And so that's basically one. I mean, so I think this was a very basic attempt to have more than one mode. I think there's more possible approaches where you could take that further. This is a bit also not very impressive shape change because the specific mechanism we chose is only an infinitesimal mechanism. So I think you could potentially take this further and really make drastic shape changes. But I haven't really seen that a lot, in fact. So and so to conclude, I will just quickly show you that if you have two modes, you can find ways to actually select the two modes as you want. So here we use fingers, but it's not very practical. So one trick you can use was to use viscoelasticity, so a material that responds differently whether you excite it slow or fast. And so by, for instance, having some bones that are very viscoelastic, so very stiff when you load them fast, but very soft when you load them slow, and some that are less viscoelastic, so that don't depend on strain rate. And so you can make a material that would then preferentially actuate the one mode or the other depending on how fast you actuate it. And that's what we did here. And it is interesting because this one has a slightly negative Poisson ratio and this one positive. So you can select the Poisson ratio based on speed. Right? Again, what I would really dream of doing is really go beyond that and maybe make a smiley face or a more advanced shape just based on speed. Right? We are now taking this idea of texturing, using this idea of texturing with viscoelasticity a bit further. Not in combinatorial metamaterials, but just in normal kirigami and oxatic. So that's what a postdoc in the group is doing, Sharam. And let me see. So on the left, you compress slow. On the right, you compress fast. Did anything happen on this video?
No, that's happening.
Ah, yeah, it's happening. So you see that here on this cube, when you compress slow, it goes in. And on the right, when you compress fast, it goes out. Boop. Yeah. And you can also do that with kirigami by patterning, your viscoelasticity of your material. You can pattern which one goes in. So potentially, I think with kirigami, we don't really, I don't really, I think, for instance, this idea of combinatorial, you could take it to kirigami, perhaps, and maybe then, for instance, use this approach of having a stimuli-responsive material or something that depends on strain rate or on heat to actually design something that has more than one shape. Yep. So that's it. I think that's all I wanted to discuss today. So, how using this idea of combinatorics you can go towards shape-changing objects, and how it is maybe an interesting library to do that. It's not the only way you can do that, but that's potentially interesting. And maybe before I finish, I just want to make a last comment is that, as I said, it's very hard to design those things. So the design that we have really, I like to think of them as needles in a haystack, right? So our rotating square mechanism of kirigami, origami are really in a needle. And and then you have like infinitely many options. But what we've done so far is just walking on the needle to change a bit the geometry. But we're a bit stuck on that needle for now, right? So that's really I think the upshot in terms of design. So far I think we're really only exploit the vicinity of some designs we know. And it's very hard to do something from scratch. Yeah. Speaking of needles, I guess I'll quickly discuss the paper of Ryan. So what Ryan did was to actually show that machine learning algorithms can be useful because it seems like they can actually learn some of those combinatorial rules that you have. And so it's a potential data-driven approaches are potentially interesting approach because, for instance, in the last case where you don't have disparity in T-ferromagnetic order, you're clueless unless you're very, unless you're luck out in the stat mech of these objects. But if you don't, maybe a go-to method is maybe to go to this data-driven approach that can be very efficient to actually explore the design space. You're still working on the needle, I think, but at least maybe you can go far, you can go further, you can explore more, right? So this is just an example of what Ryan did to show that this is a classification of whether something folds or not, and this is just this confusion matrix that tells you that when you're on the diagonal, you're successful, and it tells you that basically these machine learning algorithms are quite successful. So it's potentially an interesting approach to actually use that as part of your optimization scheme or design scheme later on, right? And so that's all I wanted to say. That's all I wanted to say for now. So with that, I'd like to conclude. So thank you. Tomorrow so I showed you a few approaches for design. Tomorrow what we'll do is, we have this object we design in a linear level, but tomorrow we're going to smash them in the lab, or theoretically also, and see that then you have to handle nonlinearities and these interactions between building blocks that makes interesting objects to study. Yeah. So thank you.
Thank you. Questions?
Quick question about the two modes that you control with the strain rate.
Mm-hmm.
After it is actuated, is there an energy barrier between moving the two modes? Or can it still move between the shape that you got compressing fast? Can it freely move to the other one?
Yeah, it does. It does. Okay. It does. You have a regime where it stays stuck, and a regime where actually you have a transition wave, a traveling wave that takes you from one state to the other. In fact, we show that the way you can describe this is through a reaction diffusion equation that takes you from one state to the other. And actually, there's some analogy with what you have in nature, like this plant mimosa that also folds. So it's kind of an example of a wave, mechanical wave without inertia, if you wish. And we also show that we can use that to transport objects. So that's actually an interesting thing in itself. Yeah, good question. Yeah.
More questions? Okay, if not, let's go to coffee break, and we'll be back at 11:30. Thanks again, Corentin.